Hello, can you hear me?
I can hear you.
Okay, I got my speakers turned on this time.
Good.
Yeah,
That
but
helps.
yeah, I can hear you too. Okay, let's see. Let's see. Where's my list of? Here we go. Okay, let's see. Now, okay, on Monday. let's- Okay, you can hear me now, right? I think I clicked
Yes,
on the wrong button. I think I actually muted myself for a minute. Okay,
you did.
yeah. Okay. Um, we've pretty much covered the fork join stuff. And I've kind of hit a bit of a roadblock. I haven't been able to find a good explanation of what to do next. Um, you know, we've been doing two kinds of parallelism. We started off with really basic stuff. We did the P threads and the basic of Java threads. Which is really low level. Okay. And it's good to know that stuff. It's good to have a sense of what a P thread is, what a Java thread is, what a mutex is, and a semaphore and a condition variable. But the trouble is, as I've pointed out a bunch of times, nobody expects you to program with those things anymore. Uh, you know, they're tremendously difficult to program with, and the whole world is trying to avoid ever having to use mutexes and semaphores unless you're the person actually writing the operating system. Okay, so you're supposed to transition to modern parallel programming, and fork join is one example we've done of this more modern. Okay, and we already saw how in a weird way how weird it is. We couldn't even get speed up on our main example, which came from this book from University of Washington, because it's just memory bound. It's not even, it isn't turned out to be very parallelizable. And then we could parallelize the Fibonacci, but that's not the most compelling example in the world, because you could write a serial Fibonacci version that's probably 100 times faster than the parallel version. Okay, because we're parallelizing the recursive Fibonacci when we should be writing the serial version of Fibonacci, which is actually super fast. That's what you find in the algorithms book. So we don't even have even these books can't even come up with a compelling example of what do you do with fork join. And I've been trying to figure out like just what the the it seems that what's really compelling, at least not with fork join, but with a lot of other things, is try to parallelize over in like network IO. Okay, but
Oh,
hmm,
I can do plenty of that.
yeah, and that brings up languages like Go, and that actually goes back to what we were doing a little bit earlier when we did these examples on polling versus events. You know, remember the events were trying to do IO operations, and but that didn't scale very well because we were able to create three threads with a lot of, because we had to create three console applications, one for each thread. So we couldn't exactly scale that up to a few thousand or a few tens of thousands of threads. So we kind of hit a roadblock there. Okay. And it's, I'm really actually trying to figure out what's a good way to explain and do examples of what people mean by modern parallelism. And people I talk to point out that it's actually really hard because a lot of times what you do is what like we're doing with fork join. You can write the code, but you'll never see it speed up, because if you want to see it speed up, you have to run it on huge problems on clusters. Yeah. So if you're just running it on a desktop, you don't get the kind of speed up that you would get if you were Google, which is a lot of this stuff was written for. You don't get the speed up unless you're running it on something quite a bit bigger. Okay. So okay. So the question is like, what's, and I have not been able to figure this out yet. What's the next thing to go look at? What's a good thing to look at in terms of parallel code? Now, Java has something in it called parallel streams, which I haven't had time to look at. Parallel streams was invented at the same time fork join was. It seems to be another, but I think it's going to have the same kind of problem. That coming up with examples you can run on your desktop that you don't see speed up. You can write the code, you can see how the code works, but you're not going to see speed up because unless you run it on massive jobs, it's hard to see speed up. So does anybody have any suggestion? Like, is there something in parallel programming you've heard of that you think would be worth pursuing?
I have done two things in parallel programming that I do know will speed up. One is image searching and filtering. And I am writing a fork join version of just that right now. I've got most of it implemented already, so I'll be quickly onto the testing phase. And also, for trivially parallelizable stuff, I've been doing a lot of network IO things.
Yeah.
Where most of my job is tuning the number of processes and threads that I queue up at once in order to load the CPU sufficiently.
Yeah.
And also text processing, which
Yeah.
also experiences substantial speed ups from doing work in parallel.
Yeah. The network IO is not really doable on a desktop because like you're doing it from a server. The text searching, that's probably something maybe we could, that might be something we can build examples out of. And
The text searches that I did are trivially parallelizable. So I did one text, like I'm a one large text search per book, because I was searching through books. So I would give one book to one thread and let it go. So there was no IPC required, except to collect the results at the end and do a little bit of processing on that.
Huh. Yeah, I wonder if the text would be a good way to like try to come up with like even I know people have done examples just counting the words in a text file. If it's a book, it would if you want to count the number of words in it, that takes time to do.
Yeah.
And, let me think.
I don't know
Some of
how
that's so
you would do it.
trivially parallelizable that we could just do that with threads. There wouldn't be any need for a high level parallel programming concept because, like I say, it's so trivially parallelizable. You just say, okay, here's 5 threads, here's 5 books, 1 thread per book. And I'm trying to think of if there's a way to make it.
Yeah, that's how I ran it, was trivially
Which is fine. Yeah, but
parallelized.
which is, but like the fork join, of course, is something that's a little bit more sophisticated. It's doing something in a, it's not a obviously trivially parallelizable thing, though it's pretty close to it. Um, but it isn't just one thread per job because we're trying to do well. Actually, that's a good. Actually, think about. Actually, maybe that is kind of a good example. Think about you have a bunch of books and you want to count the words in them. One of the
Hmm.
books is like a 100-page book of poetry, and the other book is War and Peace. So one thread does the book of poetry, and one book does War and Peace, and that's not what's wrong with that.
I mean, not
See,
necessarily much.
well, no, terrible load balancing.
Yeah.
See, so that's where that's where that would make the problem interesting now was because see that would have terrible load balancing. One thread, one process, unless you had a lot more books to do.
See, that's what
Yeah,
I
if
had. I
it
had
would,
42,000 books,
right.
and I
So
used
if that
Parallel, which did load balancing
and
for me.
that's kind of like what that's the point of the fork join was to have lots of little pieces of work so that when one thread got finished with its share of work, it could always go grab another one. And here, if you had a lot of books, it wouldn't matter if some were long and some were short. Every time a thread did a short book, you just have to make sure that that thread would pick up another book.
Hmm.
Okay? But if you just had two threads and two books, and one was long and one was short, yeah, now you have an interesting load balancing problem. Like, how could you have one thread step in and help the other thread in the middle of its book?
So the question becomes in this case, can you get a way to start reading a file, let's say in the middle of it?
Well, you can, but the yeah, but the idea might be like what fork join is you try to chop up you're gonna you might really want to think about how could you divide the work up into pieces ahead of time.
Hmm.
Yeah, like for example, you could load the books into arrays and then give threads chunks of the arrays.
I mean, the
So
problem with that is that you can count words in a book way, way faster than you could ever load it out of the disk that it's sitting on.
oh, you have to read the disk to be able to count the words.
Like one thread, like if you have one thread sitting on a book reading bytes out of it, most of that thread's time is going to be spent idle waiting on IO.
Yeah, that's always the case with IO. That's yeah. Hmm. And that right. So that actually begs the question, should you give one thread to what should you give one book to one thread? Maybe you should actually give 5 books to one thread so it could be reading while it's waiting for IO from one of its books, it could be processing the IO of another book.
That's an idea. I also thought maybe instead of having multiple books to one thread, you could have one thread read a book from multiple locations.
Why would you do that?
You might be able to read it faster. I'm
Oh, but it
honestly
have to be
not
stored.
sure.
I mean,
If
if there were actually several places you could read it from.
if like say that you were reading it out of a RAID array, like say a
Hmm.
RAID 0 array, that might make sense to do, especially if it's SSD based where you can
Hmm.
grab those chunks out of the array very, very, very quickly. So that might work, but out of a spinning disk,
Well, if it was a spinning disk,
honestly, it wouldn't make sense to do
well,
either one of those.
no, it would be, yeah. Out of a spinning disk, it'd make a lot of sense to have to give each thread a bunch of books, so that while it's reading one block, while one thread is blocked reading a bunch of text from its file, that's well, the single suppose the thread is processing 5 books simultaneously. It would queue up, say, a bunch of IO operations. Okay. And then hopefully, as soon as one of them returns, it could spend its time processing the data it got from that IO operation, then queue up another IO operation. By then, hopefully, another IO operation is completed. So it could keep itself busy processing data while it's got, say, 5, 6 IO operations pending. Now,
So-
this is actually what the Go programming language is exactly what it's trying to solve is problems like this. What we're talking about is a more realistic sense of what you would be trying to do. So, Andrew's example is a good one. You've got like 1,000 books on your hard drive, and you want to somehow process them. Maybe just simple, count the number of words in them, or just ask, in my 1,000 books, how many times does the word, you know, evangelism appear in my 1,000? How many times a book. What's the probability that a certain word appears in any of these books? Okay, so you got this big calculation you make across 1,000 books. Reading a book is very IO intensive, but you have to queue up IO operations. But at the same time, once you got the data in your memory, then you have to do a very labor intensive compute bound calculation. So you've
mhm,
got tons of IO to do and tons of calculations to do. And
mhm,
scheduling that is not a trivial matter. Like if you just give each book to a thread, okay, then that thread's going to actually waste a massive amount of time waiting on IO with nothing to do. So then you go, okay, so let me give each thread, well, how many books should I give each thread? Is 5 books enough, or does each thread need 100 books? But then I'm trying to do complicated scheduling, trying to figure out, well, how many books should a thread have so that it doesn't waste any time where it shouldn't be doing too many IO operations, but it shouldn't ever be sitting around blocked on all its IO. Like 5 books may not be enough. You give a thread 5 books,
mhm.
it issues 5 IO operations, and then then it has to
Yep.
wait for at least one of them to finish.
For something like word count, you're going to be strictly IO bound.
Right,
After
right.
a
So
certain
you
point,
probably want to do a certain. But let's imagine it's a more where when you've got the. Let's imagine a situation where when you've got the data, you have to do something more complicated than just count words. So let's imagine that there really is some calculation to do, like search for a particular word. So you're searching for a particular word to see how often it occurs in all these books. So you're alternating between a fairly computational process that has to that can really work hard on the CPU when it gets its data, but then as soon as it's gone through its data, it has to do an IO operation to wait for more data. Okay, then you've got a complicated scheduling process of scheduling IO calculations with compute calculations. Okay, and that's actually the model that modern parallel programming is trying to come up with. Uh, Java, in the case of JavaScript, what it's trying to do is balance a web browser loading tons of data from a web page. Modern web pages have you download so much stuff. So there's all this IO bound stuff, but every once in a while, like when a JPEG gets downloaded, it has to be painted on the screen. So then there might be a lot of calculations to do.
mhm,
So part of what's like fork join doesn't solve. Fork join is an example of not what we're talking about now. Fork join was designed for purely computational parallelism, but a lot of the modern stuff, like the Go language and modern JavaScript and even some of modern Java, is trying to balance the applications that have a lot of I/O and a lot of calculations. How do you schedule all that in a way where you don't tell the programmer, it's up, you tune this, you keep playing around with this, you keep trying to figure out how many books you should give each thread. When you do an IO operation, should you ask for 1,000 bytes at a time? Should you ask for 1 million bytes at a time? What's the appropriate chunk of IO to request at a time? How many IO operations should you do at once? Right? So there's a bunch of tools that modern parallel programming tried to try to give the programmer to do this, but it's not real well explained. And,
one way that I solved this issue to avoid complex IO scheduling was to stream the data. So
mhm.
I would use a tool like Cat, which would start grabbing data out of the drive and feed it through a pipe into another program. And that program would start counting the words as they go by as cat is pulling them out of the hard
Yeah,
drive.
and Java has streams, and Java has what are called parallel streams, and I've been trying to find good explanations of some of this stuff too, because I think that's actually one of the things they've latched onto overall is that streams are a good idea. Yeah, the streams that having a stream of data is a good way to think about the data. So it's a lot like pipes on the on the command line. You know, it looks a lot like pipes, but it's more abstract than just command line pipes. So you're trying to do streams in a more abstract sense than just streams like on standard into streams in the command line. You're just like you're connecting standard out to standard in.
Yep.
Yeah. Here you would have, you know, Java lets you create arbitrary streams, and you can connect these streams together. Okay, so that's another one of the modern ideas. But then I guess trying to find good explanations of this, I I'm not being successful at finding what I think are good explanations of some of these ideas. Every time I keep reading lots of people writing kind of high level explanations without real code that you can run, and real examples that are compelling. You know, the code is pseudocode and the examples are not compelling, and trying to find, then if you do find a real example, it's 1,000 lines of code. Yeah, and trying to find something that's digestible and yet interesting is what I've been trying to find and haven't had. Yeah, as all, we've entered a modern period now with parallel programming. The first half of the course, we did the really basic stuff, P threads and Java threads. We could have done that the whole semester. There's lots to talk about there, and there's lots of books about that. There's no lack of books that explain that stuff. It's just that it has the disadvantage of being not what you would get paid to do these days. The more modern stuff has all been pretty much developed in just the last couple of years, probably I'd say the last somewhere around 5 to 10 years, but it still doesn't seem to have the kind of description that I was hoping that I could find. You know, I'm not finding the kind of description that we could build a course around. Okay, so like right now, I'm not sure what to do next. There's two possibilities. One is to go back to P threads and Java threads and just do low level stuff some more, because there's a lot of low level stuff we could talk about: readers and writers, barriers. Uh, you know, there's a whole bunch of low level threading and parallel programming concepts that you can talk about, but you'll probably never. They're interesting from a kind of purely intellectual point of view, and you'll probably never see them used. You know, they're actually buried deep in, you know, they're buried deep in the libraries that you would use these days, but you know, only a small number of people would be maintaining those libraries and actually having the need to know how those things work. And then the other possibility, again, you know, besides going back to the low level stuff, would be to try to find some, well, a good example is fork join. Fork join is a nice example of a higher level modern parallel programming. We saw what the code looks like, you know, and we actually have a good sense of how it works. We've described it, you know, the references we have describe it well, but the examples aren't so great, you know. So the idea behind it is described well, but I'm actually not even finding it, you know, I'm not finding something that's as well done as this fork join. Even though the concept was explained well, the examples were a little bit, you know, underwhelming, but the code, the idea was well explained. Like, I'm having trouble finding a good explanation of parallel streams. I think that's logically that would be like maybe the next thing to do would be talk about Java's parallel streams, but I haven't found a good explanation of that yet. I'm still looking. Um, So I'm not sure really what, if we should go back and do low level stuff, which there's tons of, or if we should try to continue to find some kind of higher level, and I want to keep with Java. We're not going to switch to like Go at this point. Like Go would be an interesting example. But we would have to start the semester at the beginning with doing Go, because that's a whole new language. Okay, and same with JavaScript. Like there's stuff in JavaScript, but there'd be no point at this point in switching languages. So I think Java is the good language to stick with, but try to find, or either switch back to low level parallel programming, or use Java to try to find another explanation of one of the more high level Java things. Oh, I give you an example. Remember this chapter 4, this modern concurrency? That's kind of an example. I mean, about stuff that's not. I mean, I was really disappointed with. I think you mentioned it. It's some of you realize it's not that easy to read, and it doesn't really explain very well what it's doing. It doesn't seem to have really good examples of anything. So it covers a lot of ideas, but never, yeah, it didn't feel like it was really explaining anything. It just seemed to be going through a long list of ideas without really, and that's what I'm finding. It seems to be that the literature is full of stuff like that that isn't like the fork join stuff was well explained. At least you got a sense of what fork join is really trying to do. This stuff didn't do that. This stuff, like this book spent 5 pages on fork join. This one spent maybe 20 pages on fork join. You needed to spend that money on fork join. You can't do it in 5 pages. This one covered way too many things, 5 pages at a time, and ends up not being, I think, all that useful. Okay. So, but I don't know of another thing besides this fork join. The fork join paper is reasonably good. Okay. Let me think. I really was hoping to go back to this example. I think this is what gets at the heart of modern parallel programming. But the trouble was the overhead of trying to create events was too burdensome. We had to write so much code down here to get 3 consoles producing IO. But the the polling versus events versus threads idea is really an important idea that um, and I've been trying to find a way to turn this into something that we could really do good examples with. I don't know, maybe the text processing can be done with this one. Maybe there's a way to go back to the polling and the events and do massive text processing doing it event based instead of just saying, because that might solve the problem of how do you balance threads versus books. You're going to search a bunch of books for something, and it seems trivially parallelizable. Give each thread a book, do one book, then go do the next book. But that's actually not a good strategy, because if a thread's doing a book, like we said a minute ago, it's really going to spend most of its time waiting for IO to complete. So you really want to give a thread a lot of books, but how many? How many books? Well, if you have a good balance between events and threads, then the events will drive the threads. The thread will do as many books as it gets told to do by events. Whenever some IO is ready, then a thread will be told to go do that event, to handle that event. So instead of assigning, the idea would be, instead of assigning books to threads, you would assign events to threads. So maybe you'd have like 1,000 books and 6 threads because there's 6 CPUs. Okay, and you would essentially start IO up on maybe 100 of the books, but then every time an IO operation is ready, you just give it to a thread. And the thread you give it to doesn't have to be the thread that was reading that book a minute ago. It's just that whenever an IO operation becomes ready, it's given to some thread. And then that thread shouldn't care. It shouldn't be that a thread shouldn't say, hey, this is not my book. The threads wouldn't need to know anything about which book the IO operation is really doing. But then you have to make sure that the event carries with it all the state. Like, that event is tied to some book. That book knows how much data is read already, So then you have to have event. Your scheduling is going to be event based, and the events aren't tied to any CPU, but the events are tied to a book. So now somehow the events have to carry what we call state with them. The events have to say, well, okay, now this IO operation's from book 6, and by the way, by this point we're halfway through the book and we found 27 instances of the board we're interested in. So now the thread can update that state by processing a little more data for that book. Then it would issue an IO operation, because when it exhausted the data it had, it issue another IO operation, but it had no way of knowing which CPU is going to end up finishing the IO operation.
We can
Mhm.
probably do the polling event stuff in C on Linux
Well, it
because
can
I
be done in
tried it out there and it's actually fairly easy. There's not a huge amount of boilerplate to do.
Well, I think Java has it too. Java has it's actually you use some things called futures, so you can use things called futures, and that may actually be a way, an interesting thing to do this. You know, look at how we could do that with Java using its. Uh, Java has what's called asynchronous IO, which is IO where you can just launch the IO and then go do something else. So you're not blocked on, that's what we were doing over here. The idea of having uh, non-blocking event-driven IO. So Java has that, and Java has these things called futures. And we might, I might be able to put together an example like that using Java, using some of the Java ideas, because this is really kind of what people are trying to get at. Because that's a good example. You've got 1,000 books on your hard drive, and you want to gather data about the words in the book. How often does a certain word appear in all these books? That's a that's a big data kind of problem, and that's actually where modern parallelism is these days. Modern parallelism is about big data. Okay, so that would be the right direction to go to kind of get a sense of how do you parallelize big data operations. So and download, books are easy to get. You can go. Did you get them? You were getting them from Project Gutenberg?
Yeah, so I made
Yeah,
a cache of all the English language books on their site. That was
yeah.
about 40,000 books.
Hmm. Yeah, and so we wouldn't even need that many, but we could download like a few hundred, or it might not be hard to come up with a cache of a few hundred or a few thousand books, and then.
I'm spinning up my Linode that contains the books right now, and I'll make a download available to you.
Hmm. Okay, how big would it be?
Depends on how many books you want.
Well, roughly, what is it? A book is a couple megabytes, right?
Usually not even that.
Yeah, yeah, because they're just plain textbooks. They're not even PDFs or. Okay, so yeah, what? How much data is all of the books? Is it a few gigabytes or?
So that's about 20 to 30 gigabytes. I
Okay,
forget the exact number. Let me
yeah,
look.
I think a good number is in the couple gigabyte range. Like to get good sense of processing, I think a few gigabytes is a good amount of data to have. Actually, and that would be after it's uncompressed, right? That would be the uncompressed size.
Yes, you
Hmm.
don't want to deal with compressed as your
No,
input.
but for moving the data around, you want to compress it.
Oh
Like,
God, yes. You do
yeah,
not want to be moving small files over a
yeah.
network individually. It's a
But
bad time.
we should. I'm thinking that all the data should be loaded on one CPU and just processed locally. Not with get rid of the networking stuff. That's one layer of complication that should just be gotten rid of. So we can deal with local IO, not network IO. Okay, so okay, yeah, that might be a good example because what we can trying to think if it's in. No, it's not. I think that would be a good little project, is to use Java to effectively parallelize searching large amount of text. I think that would be a good example for us to do. So, and trying to use, but not using low-level threads, hopefully using reasonably good, simple to use modern parallelism. Now it's not going to be fork join, because fork join is not good for I/O processes like this would be. But still use something that's reasonably high level that comes from Java. Okay, and I'm thinking it's going to be the Java's asynchronous I/O, and I think probably what Java calls futures. Okay. Okay. I think I have a reference for the non. Yeah. Uh, when I wrote this version down here, the problem down here is I was writing low-level Windows code. That was another problem down here. When I was trying to do events and threads, it was very low-level Windows code. That's why the code was line after line of tricky Windows function calls. So that needs to be, we want to do something similar to this, but brought up to a higher level using Java's nicer libraries, Java's asynchronous I/O library, and Java's ability to I think use these things called future tasks. Okay. Um, um, Let me tell you what. Um, at, there's a modern one of the pieces of modern parallel programming are what are called futures and promises. But if you see, uh, Wikipedia in here, asynchronous programming futures, that's the Dart language. Okay, almost all modern programming languages, if you go through this, Java, JavaScript, Dart, Go, C, not C, C++, they've all added something called futures and promises. It's an interesting idea, and I think we can make use of it. Okay, I want to. No, here's what it kind of works like. Suppose I have int x equals f of y. Okay, that's a function call. Okay, now you can make that into, you can think of that as Java, C++, or C. Okay, now the way you think of that is the code jumps into f, computes f, then it returns and gives you x. So that would be what we call a synchronous function call. Okay, now if you do this, now this is not really that, but if you do something like x equal int x, if you, well, suppose instead of calling, I mean, a thread, remember, a function can be either used as, if you can call a function synchronously, or you could start a thread in it. Okay, so if you start a thread in it, so if you say something like create thread f with parameter y, okay, so using like a pseudocode here, you could say create thread, but then how do you get the result from it? If you can't write this. Okay, this would be kind of a weird thing to write. Okay, up here you're saying that call f, when it returns its return value, put the value in x. Here you're kind of trying to say run f with input y. Okay, and what you'd really want to, now notice if you did this with real create thread, this holds the error condition, whether the create thread succeeded or not. But what you really want to do is something that says, in the future, when this guy completes, take his return value and stick it into here. Okay? Now, modern Java actually can do that by having the type of X be something called a future. So you'd say X is a future of type int, okay? And it will hold the result of this asynchronous call, okay? So this is the kind of the core idea behind what, when you Google programming futures and you see these promises and futures, it's the idea that you will say that this variable, there's different ways to talk about it. You can say that it's a promise to hold the result of this thing when this thing is done, or you can say that this is a value that will be valid in the future sometime. Now, if something's a future, how do you know when this thing has actually got a valid value in it? Okay, so the future interface provides a couple methods. So, for example, you could do the following. You could say int done. Well, okay. In Java, the way it would work is if this is a future, what it really is at some point this thread will complete. When this thread completes, there'll be a value in here. Now, instead of in the way we've done things before, we would join on that thread, and then when we joined on that thread, we would know when this value is actually ready. But in this point of view, instead of joining on this thread, you let the return value of the thread be stored in this thing called a future. Then at any time you want, you can call get. Now, what get does is get's like join. Get would block you until this guy is done. But that may not be what you want. Okay. You may just, there's another function in the future interface. You could do the following. You could say, if x dot is done, you could ask, is the future done or not? If the future is done, you could then, for example, get the value. You could, if the future is done, you could say, okay, int, okay, you could say w equals x dot get. Okay. Now, if you know that the future is done, get was, you won't block when you call get. If the future isn't done, you do something else. And then you maybe loop back and check the future again. So in fact, what you probably would do is you do something like this. While it's not done, do something else. But then when it is done, you can go ahead and grab the result. Okay. This is a style of programming that's becoming really prominent in JavaScript and some other languages. You ask for something to be done asynchronously. The results stored in a future. Okay. This is almost like the polling idea. Notice that this is very much almost like a polling idea. Then you just say, oh, is it done yet? If it's not done, do something else. Then you go back and say, is it done yet? If it's not done, do something else. Is it done yet? Oh, it's done, so now I can get the value. Notice that with this idea of a future, see, we talked about this idea of, at a low level, of events, polling, and threads, futures look a little bit like polling. Okay, if you could make one of these threads to no, what you would probably want to do is, like, if you were trying to search a large amount of text, you would have one of these futures represent not the processing of an entire book. You'd have one of these futures probably represent the processing of a small chunk of one book. And you might create thousands of these futures. In fact, these futures are a lot like the tasks in parallel fork join. In parallel fork join, you would take a problem, like summing an array or sorting an array or computing the Fibonacci, and you break it up into sub pieces, and then you would essentially have the sub pieces computed later. Okay, so here this is saying have the work done later. See, when you create the thread will just get scheduled by the operating system at some other point. Okay, now you don't really want to do this with a thread, though, because a thread, we saw what happened when we created too many threads in fork join. Remember, when we forked lots of threads, we ended up choking the operating system. So this would really be more of a create task, something lighter weight than a thread. That really should be something more lighter weight than a thread. So we really want something that says, create a task for me, put it in, for example, some kind of like thread pool. Maybe this puts the job to do in a thread pool like fork join, and let me get the value in the future. In the future, I'll get the result from, but see, instead of putting, here in the fork join, you put all these tasks in the pool, and then you got one answer out of, and when they were done, there was one answer from all of them. Here, it's more like you have lots of individual tasks with each individual answer, but you still want them essentially put in a pool. There's going to be a task pool, and you just want to be told when that particular task has got an answer for you. So his answer is stored in a future, and then you could do something like poll that future when it's done. Okay? So this is one style of programming I think that would be interesting to look at, because it's becoming ubiquitous. Let me show you. Okay, if you Google okay, there's JavaScript futures. Actually, okay, there's futures in Java, there's futures in JavaScript, there's futures now in C++. See, C++ futures exist. There's futures in Rust, if I remember right. Rust futures. Rust has futures now. Futures have become a big deal in the last few years. Almost every language has implemented this idea of futures. Java, Rust, C++, JavaScript. I think Python has them also. Okay. Python has a futures package. Okay. So that's an example of something that's fairly recent in the last few. I mean, some of this is only in the last year or two. I think Rust got futures real recently. I don't know if it says here when they were added to the language. My memory is that it's very recent. And if you notice, you'll almost always see mentions of futures with asynchronous IO. Okay, because the futures are very much used to do this, what we were trying to do a little bit earlier, blend polling, events, threads, and IO. It's how do you blend polling, events, threads, and IO. Okay, so almost every time you look up futures in any of these languages, you see them mentioned in some kind of terms of asynchronous IO. Okay, so JavaScript has them, Java has them, C++ has them, Rust. I think C++ was another one that got them real recently. I don't know if this will say when C plus when. No, they don't say when it was added to the library. Okay, I know it's in just the last few years. Okay, and it's become a very important. The idea of programming using futures. See, does it say when the what library? Well, I think it was C++ 11. So that means it was added 8 or 9 years ago. Okay, so it was something that was added probably in the last 8 or 9 years. Okay, now 8 or 9 years seems like a long time, but it's amazing how long it takes for these ideas to percolate through textbooks and become something that you can really, something that you can find good references for, as opposed to just being told go read the source code. Okay, it's not so easy to find good references for a lot of this. Probably the most references are JavaScript. If you look up futures in JavaScript, you'll find gazillions of web pages about them, because they seem to become very popular in the JavaScript world. Okay, so I've see lots and lots of references to JavaScript futures. Okay, so I think we could maybe write some kind of parallel text processing programming using this, built around these kinds of ideas of, instead of creating tasks and putting them in a fork join pool, we could build up tasks and do, the task could then be a mixture of IO operations and compute operations. IO operations that read in chunks of a book, and then compute operations that process a chunk in the book. So yeah, we would want to find something that would do the scheduling semi-automatically by making use of this kind of stuff here, instead of us having to think real hard about how many threads should we have, how many books should we assign to each thread. Something like this might make it more straightforward to get a parallel programming written. Okay, all right. Okay, now what I'm going to do is I'm going to try to find some good references for this stuff and try to write up an example, and hopefully I'm hoping that maybe by Monday I'll have something that I can show you that would try to do something that would be, I think it would be back to this idea here, this combining asynchronous IO with threads and trying to handle events. Okay, but do it in a more modern Java form that uses probably something along the Java asynchronous IO and Java futures. Okay, all right. Now, um, okay. Um, does anybody have any questions about what anybody have any question about the fork join? Was there anything about the fork join that somebody had a question about that was still? Okay. Um, I'm sorry, what? Oh, we couldn't hear you. We couldn't hear, if you're asking a question, I couldn't hear the question.
Oh, sorry, no.
Okay. I thought somebody was talking, but I couldn't understand what they were saying. Okay. Um, okay. Well, that's all I can think. That's all I have, sort of semi prepared. Okay. So, I'll try to put up a reading assignment up here to try to point you in the direction of, I'm going to try to find something that explains. what's interesting, I think this idea of futures is an interesting idea. I'll try to find something that maybe points in that direction, and we'll see if we can come up with writing some kind of nice parallel application, doing text searching, and then something that would look like big data. The real issue is to make something that looks like we're processing large amounts of data, because that's where the real modern parallelism is. It's all in big data, and then we'll see if we can do it in an interesting way. Okay, I mean, another possibility is to use one of the big data frameworks, but I don't think there's time. Like there's MapReduce and there's Spark and Hadoop. There are these big data frameworks. The thing is, they do all the parallelization for you. Okay, so when you use those libraries, they actually do the parallelizing. And I think what would be more interesting for us is to see how they would do the parallelizing. So if we could do some kind of big data operation ourselves, we should parallelize it, as opposed to just saying, oh, we could spin up Spark, or we could spin up Apache Think. There's a whole bunch of modern big data frameworks that do the parallelization for you. But then that just begs the question is, what are they doing to parallelize things? So I think that's what that'd be more interesting to understand, is how are they parallelizing things? Okay, so we'll try to do something like a big data operation, which I think processing text would be a good one. Okay, unless I come up with some other good idea for a big data operation. I think processing large amounts of books would be a good. And then we'll see how we can, make use of all the cores on our CPU. Like in this case, yeah, I've got 12 cores in here. I should be able to write something that's just like fork join. We saw fork join make use of all these cores. That was nice. The examples weren't compelling, but they did make use of all the cores. But we weren't getting much speed up. It'd be nice to be able to see how we could actually get real speed up. Okay. All right. Unless anybody has any more questions, and Andrew, send me information about if you have the books. If you have the books already, I'm sorry, Ashok, do you have a question?
Yeah, yes, sir. Uh, in fork join, I understand that when we are splitting an array into the number of CPUs that we have, the number of cores. Let's say we have eight core machine, and we are splitting the array into 8 core machine. So we are giving one threshold value, like 1,000 or 5,000.
Well, we don't split the array into 8 pieces. If in fork join we have 8 cores, we don't split the array into 8 pieces. We try to split the array into thousands of pieces. What we have is exactly 8 threads, but the array gets split into if we have 8 threads, we're still going to keep splitting the array until we get to this size here, the sequential cutoff. So if we started with an array like here of 100 million, we're going to end up with lots and lots of pieces. The array is going to get cut up into 10,000 pieces of size 1,000. Okay, so when we have fork join, we have 8 threads if we have 8 cores, but we cut the array up into lots and lots of little pieces. You see what I mean?
Yes, understood. I got it wrong. Yeah, understood, sir.
Yeah.
That's
So
right.
yeah. Now, if you cut the array, remember, if you cut the array into 8 pieces because you have 8 cores, that doesn't sound like a bad idea, and it actually works fine. But it has the potential of leaving one of the cores unused if 3 cores finish early and 5 cores are still working on their chunk of the array, then 3 cores aren't helping. So remember, the key idea was we want the array chopped up into like thousands of little pieces so that we can keep all the cores busy on little pieces. Because it's kind of counterintuitive, because it would seem like 8 cores, cut the array into 8 pieces, give each piece to an array, give each piece of the array to a core. And but it turns out you want to cut them up into little pieces so you get better load balancing.
Yeah,
That's
so
going to be
work,
this. Hmm?
yeah, understood. Work stealing will come
Right,
into
works.
progress.
And the thing is, if we want to process 1,000 books, it's going to be the same idea. We don't just want to give one book to a core and say, you do this book, and give another book to another core and say, you do this book, because then we're not doing properly good load balancing. What makes this stuff hard is not parallelizing, it's parallelizing with good load balancing. And that's actually one of the real interesting ideas. It isn't just can you parallelize this, but can you parallelize it in a way where you get good load balancing so no CPU is being left unused. So no CPU is idle while there's actually work to be done. Okay, so
Yeah,
load balancing is the crux of the matter. Okay, so
yeah,
mhm.
yeah, understood. I thought work stealing we are predicting the threshold value number.
Say again,
Uh,
with word
I
stealing?
thought we are predicting the threshold value, sequential cutoff number. So I thought that create problem, but I understand that it creates multiple array created into multiple pieces and assigned to each core when it is available.
Yeah, when it's available. Yeah, when
Yeah.
when a core becomes free because it did its job, it goes to the work pool and just grabs another little piece of work to do. And and if the little pieces of work are small enough, then every core will, well, there'll be no core is going to be stuck doing a big job while other cores are left with nothing to do. Okay.
Yes, understood.
Okay. Okay. So yeah, Andrew, you can let me know like where like what kind of data, like a good example, like a good kind of problem that we could do. Like, what are a bunch of books, and what would it be like like we could do statistics on the book. Maybe what are a good example of something to process the books with. It could be word searches, it could be, I think I bet statistics would be good, because that we want something that balances balances IO with calculation. So more than just word count, maybe some kind of statistics on the word, like what's the probability a certain word shows up. Yeah.
Mm-hmm.
What's the you can do interesting thing like what's the probability, how often do you have sentences of more than so many words? Like Hemingway was famous for lots of short sentences, and other writers are famous for lots of long sentences. Like, what's the distribution of sentence lengths?
So I've done this project before. It was my final project for data mining and also for statistical computing. That line of thought of coming up with tests for this kind of a data set is a absolute bottomless pit.
Well, we just want we just want one little thing off that bottomless pit. We want
Well, I've
one.
got about 5 of them
Yeah,
already.
yeah.
Already coded.
Yeah. Well. But what I want to do is try to write them in Java. Yeah.
All right.
Yeah. Write them in Java using Java's notions of modern parallelism. So that's our goal, is to try to translate them into modern Java parallel, and then we can run them on our desktop machines, our laptops. So everybody could run them on their laptops and play around with the code. So the goal, I think, is to have it in a form of modern Java. Okay. All right. Okay. Well. Okay. I'll try to put up on the website something for you to read. I'm going to try to see if I can find a reference on this that would explain this kind of modern way of doing things, and then I'll try to write some code that we can play with. Okay. Yeah. And okay. Okay. And then okay. So, and if you want, I read. You can, if you're interested, look up futures. Like, look up Java futures. Maybe if anybody finds something they think is a good reference, you can let me know. Like, Java has futures. There's it's an interface, actually. Yeah, because remember, it's an interface because, as I was saying here, it has to provide a is done and a get method. So it's an interface, and There's is done and get. Get will block until the future is done. Is done lets you ask, lets you poll. You also can cancel a future, because if you launched 5 futures and you just want to see which one gets done first, and then the other, so one common idea is that when one future is done, you may not need your other futures, so that you can cancel them. Okay, so you have a couple. Basically the future, the interface to a future is you can cancel it, you can ask if it's done, and you can get its value. Those are the 3 main methods in a future interface. And roughly you use it this way. You create a future that's going to hold something in the future, then you could poll it till it's done, and then get its value. And then if you have other futures pending that you don't care about anymore, you can cancel them, which will essentially kill their thread. Well, it depends on what the future really is. If it's a thread, it could kill the thread. If the future is really just something sitting in a work queue, when you cancel it, you're just going to have it removed from the work queue, so that it'll never get to the front of the work queue. So the canceling could be either actually killing a thread that's actually running, or canceling could be remove it from a work queue so it never gets scheduled. Okay, so try to look up examples about futures, and I'll try to come up with a good example that uses them. Okay, so anybody have any questions? Okay, so I guess I'll do is I can just end the meeting here. If you have questions, send me emails. If you come up what you think is a nice example of, if you see some Java code that you think is a good example using futures, especially if it's something that does this kind of text processing, let me know. Okay, so I'm going to end the meeting. Pardon me?
So Kraft, I should have a link to a compressed copy of all of the books in about 20 minutes. It's an 8 GB zip file.
Okay, that's not bad. Okay, will you have it up on a server somewhere?
Do you want it up on like a Google Drive or something like that? I don't think I can email that to you.
Oh, no, actually, no, share it through was Dropbox or something like that.
Yeah, I'm gonna put it up on Google Drive because I have a large account.
Yeah, that way that's the most efficient way to send it, make it available make it available on a Google Drive or on a Dropbox or something like that. Okay, that would be great. Okay, yeah, that would be great. How many books are in there?
If I remember correctly, 30 to 40,000.
Good. And is it most of Project Gutenberg?
Or no, it is every single English language book on their site.
Really? That's all? 40,000 only? I thought they had more than that by now.
Well, they do, just in other languages.
Yeah, because if you think about it, your average American library is going to have more than that many books in it. So it's nice to have that many books free on the internet. But if you think about it, it's actually not that many books.
It's a small library, basically. Like it's a small public library.
Yeah, it would be a small brick and mortar library. That many books. Okay, but they're limited by what's in the public domain. Yeah. Okay.
Yeah, and copyright laws in America being what they are, it's going to be a long time before that number grows.
Yeah, but that would be a good start. Yeah, that might be a good starting point for doing good big data type stuff. Yeah, it might make for a nice, interesting big data type problem. Okay. Okay. Yeah. So let me know when you got that link, and then we'll keep in contact and try to find some nice. The key is to do it in Java.
This is going to be considerably harder in Java. Java, as far as I know, doesn't have the really, really nice text processing facilities that R and Bash, which are the languages that they did this in, have available.
Yeah. Okay, we'll see. Yeah. Well, it's got regex, so maybe
It does. I've used it in Java.
Yeah.
It's not fun.
Yeah, I know, but regex is never fun for anywhere. Yeah, but yeah. So we'll see about hopefully we won't get bogged down in text processing. We can keep it higher level. Worry about parallel programming and not worry about text processing. We'll see. I hope it. Yeah. So come up with something. We need to come up with a good algorithm that's kind of computationally intensive, but not make us spend a lot of time learning about regular expressions. Yeah.
Okay.
Okay. Okay, I'm going to end the meeting now. Okay.
Okay.
Bye.
Bye.